Mostly, we've been talking about computers that you can talk to and answer questions about text. But is that the extent of our ambitions? Let's take a look at this clip from Stanley Kubrick's 2001.
Have you been doing some more work?
A few sketches.
May I see them?
Sure.
That's a very nice rendering, Dave.
And even beyond the fanciful dreams of future artificial intelligence, there are people today who could really use help answering questions about images. For example, the VizWiz project from Jeff Bingham connected blind users with a question answering system over images. Here's Tom Decker, who is blind, showing off VizWiz.
So now we have VizWiz, which I'll open.
Take a photo. Use the camera button to take a new photo.
Okay, so use the camera button to take a new photo. I'm going to get positioned above these things so that they're nicely viewable.
Camera button. Record a question. Use the record button to record a new question.
Okay, I'll record a question.
Back button. Record button. Start and stop recording a question.
What color are these two socks, and what color is the one that's folded in half?
As you'll see, compared to the other datasets that people are training question answering systems on, we're nowhere near the ability to answer these questions. The VizWiz project is what's called a Wizard of Oz system. It's a human pretending to be a machine.
Oh, pay no attention to that man behind the curtain. The great Oz has spoken.
And these workers are hired on Amazon Mechanical Turk, named after another human pretending to be a machine.
It took about a minute and a half. Now let's see.
Back button. Folded sock is black. Other one is half white, half gray. Divided down the middle. Web worker. New answers available.
And there are other use cases where it's not a question of ability, but of volume. You might be responsible for watching lots of camera feeds, and a visual QA system could quickly narrow down things that are interesting from huge quantities of data. For example, I could look at my doorbell footage and ask, when did my newspaper come today? Or who took my Amazon package? So let's take a step back from those fanciful ambitions and take a look at the real data sets that are out there for training multimodal, multimedia question answering. The most prominent is VQA, or Visual Question Answering for short, which has become nearly synonymous with this girl wearing a banana mustache. This dataset set up the paradigm of looking at a picture and answering a question. The crowd workers who wrote the questions were in the Manchester paradigm, since they knew the answers, and were instructed to write questions that a human could answer but a robot could not. While this has the flavor of an adversarial setting, there wasn't a specific adversary. The workers had to have their own mental model of how to write an appropriately difficult question. And as a result, just like in many of the other datasets we've looked at, there were some shortcuts that the models could take. If the question asked, is there a, in the question, the answer was almost certainly yes. And if there was a sport involved, that sport was almost always tennis. So to correct those issues, VQA 2.0 paired two pictures together so that the answer to the same question is different in each of the two pictures. So, for instance, here, the man or the woman is wearing glasses. This makes it so that the dataset is intrinsically balanced, and the model can't just win through a text-only baseline. So, can models answer these questions? The accuracy has been climbing by 14 points over the last 4 years, getting near 80% accuracy. So what models are behind these impressive numbers? Like with text, transformers with Muppet names like Oscar, Bert, and Ernie are to blame. But how do transformers deal with visual input? Thus far, we've only been talking about words and word embeddings. Just like you need to split a sentence into word pieces, the first step is to break an image into pieces that correspond to objects. Now, I don't know how this works, and even if I did, it would be out of scope for this natural language processing course, so I won't talk about how all these fancy boxes came about. But once you have these boxes, you can then embed those boxes through a linear or nonlinear transformation of the constituent pixels, which, unlike words, are inherently continuous. and already a vector. Just like words have an embedding based on the word's type and the token's position, the visual word embeddings are also a function of the pixels and where the pixels were located in the original image. So then you can get a combined visual and text representation of an image caption or an image caption pair. And because a transformer isn't tied to the strict linear order of a sentence, thanks to its attention map, it doesn't really matter in what order you plop down the objects. Okay, so how do you pre-train transformers with visual and text input? First, you can do masked word prediction just like you did with text-based BERT. And if you can do that for words, why not also do it for objects? Finally, just like we did next sentence prediction for text representations, we can match images with their captions. So the models, after you get past object recognition, look a lot like our text-only models. I think you'd agree that visual question answering can be quite a bit harder than text-based question answering. So why are the accuracies so much higher than for text-based question answering? That's because all of the questions in VQA are multiple choice. It basically boils down to selecting which of 4 answers is correct. And it's just not VQA. Other visual datasets are multiple choice as well. And while some of the other datasets that we've talked about are implicitly multiple choice, if you ask Squad when something happened, it's essentially multiple choice among all the things that look like a date. And while other datasets are implicitly multiple choice, if you ask Squad when something happened, it's essentially multiple choice among all the things that look like a date. But it's not as clear-cut as VQA, where there are explicitly 4 choices you need to choose from. And datasets like QuizBowl are a multiple choice task over tens of thousands of possible entities. So why is question answering over images always multiple choice? Because we have a hard time agreeing on what the answer should be. We saw this before with long-form question answering, and even for factoid question answering, you need to be sure that you have all of the relevant names for an item enumerated. Because we don't have text to ground the answer, again, which makes text-based question answering more like multiple choice, even for everyday items, you need to figure out what name to give something. What's Mr. Burns wearing here? What should he call this? Mules? House shoes? I personally think that some of these options are better than others, but arguably all of these should be acceptable answers. And Mr. Burns seems to prefer slippers anyhow. This isn't just a problem in English. Here's a map for what slippers are called in the German-speaking world. Naming things from a picture is hard. Describing what a thing is doing is even harder, and harder still is describing interactions. What's Mr. Burns doing to his slippers here? Is he dancing, bouncing, flaunting, tapping? Given all of that flexibility, evaluating whether an answer is correct is just generally hard, as we've seen many times before, without text to ground you. And oftentimes when we're interacting with visual information, it isn't just a single image, it isn't static. Often we care about answering questions from moving pictures. In other words, movies or television. There have also been datasets about these questions as well. Just like VQA, these are multiple choice. But does that mean you need to watch the movie to answer the questions? Not necessarily. Movies often have closed captions, subtitles, audio descriptions, and scripts. Just in case you're not familiar with these, we'll talk about them a little bit to tell you what they are. Captions are the text that appear at the bottom of the screen and are available for people who are hard of hearing or just want to be able to also read what the person is saying or what noises are happening. They're not always perfect, but they usually get the point across. It's a lot of work to get captions right, but it's worth the effort. While captions were first intended to make movies more accessible for the deaf, audio descriptions were created for the blind. For example, here's a clip from Frozen.
His nose lands on a frozen pond. A reindeer looks up and pants like a dog. Seeing the reindeer slip on the ice, the snowman smiles and moves towards him.
The description explains what's going on in the movie beyond the dialogue. While humans typically get this through audio, the descriptions were written down at some point, and so these can be provided to the computer as text. Finally, most movies and TV shows start as a text called a script. These contain not just the dialogue, which gets turned into captions, but additional information like where a scene takes place, and the instructions to the actors about what they should be doing. While not as verbose or as beautiful as the audio descriptions, it nonetheless provides a way of interpreting the raw audiovisual representation of a movie in a form that is easier for a computer to process. Here are two datasets, Movie QA and TV QA, that have questions, multiple choice of course, based on movies and television. And just like how you can insert both visual and text information into BERT, you can feed in recognized objects, the captions, called subtitles in this figure, into BERT. And then you can answer questions about temporal relationships, about what's happening in a given scene. Some of this looks a lot like how you do machine reading questions given a context. But the other kind of question answering that we saw for text was open domain question answering using systems like DPR. Does something like that exist for visual settings? Yes, and just like for dense passage retrieval, where we had an encoder for the context and an encoder for the evidence, we can try to do the same thing for images and text. Try to learn encoders such the encoding of the text description and the encoding of the pixels in the image are as close together as possible. As I record this in 2022, there are two big models that are doing this, Clip from OpenAI and Align from Google. They both have fairly similar architectures with dual encoders. And with this sort of architecture, you can do things like find captions for an image automatically, or given a search string, find appropriate images for that search. A lot like the search we do for answers to a question. As I wrap up, I hope you've noticed the pattern here. The tools that we created to help people with visual or hearing impairments end up not just being a good idea for everyone on Earth, but they're also one of the key tools that we're using to build up computers' ability to understand the interaction between text and images. And maybe we'll have AIs that can sort everybody's socks and then answer questions about it afterwards. This future can't come fast enough. This is just a single lecture from a course. YouTube likes to show you these videos out of order, but if you go to the course webpage linked below, you can see the lectures in the right order, and you can get resources like homeworks or suggested reading. You can also visit quanta.org if you want to learn about our systems for creating computers that can answer questions, where Quanta stands for question answering is not a trivial activity. If you want to help the channel, provide a big gradient to the algorithm by liking and subscribing.